G'day, in this video we're going to be unpacking latent heat. So we're looking at dot point 3.5.5. It's the final thing that we're going to be doing to tie together our thermodynamics part of this module. We're looking at temperature, thermal energy, particle motion, and how that's all related. This particular content statement is focusing on the concept of latent heat, which is used to describe and predict change of state. So in this video, we're going to be looking at defining latent heat first, and then applying that latent heat formula, which we'll see in that definition, to various scenarios. So usually when we talk about latent heat, we're talking about heat energy which makes a substance change state rather than change temperature. Generally speaking, when we put energy into a substance, it's going to cause an increase in temperature. However, once we get to a particular point, the energy that's being input will no longer increase temperature, but rather lead to a phase change. So at this point, temperature will even out, but the object will go from solid to liquid. Once we have a complete liquid, the energy that's being input will again cause a temperature rise until we hit another threshold. And that's going to be where, again, there is a phase change. Temperature doesn't change, it flattens out, but we go from liquid to gas. Then we begin to add more and more energy, and again, the temperature of the gas begins to rise. Essentially, here at these points are our melting points and boiling points, the point at which a substance will melt and the point at which a substance will evaporate. In these sections in blue, we can analyze what's happening to the energy by using the specific heat capacity formula. In other words, using that formula to analyze the amount of energy that is being input to the substance and the resulting change in temperature. For the sections in red, though, the specific heat capacity formula doesn't hold up. We put energy in, but there's no change in temperature. And here we need another relationship which describes what we call latent heat. And again, this is the heat energy that is leading to this change in state of the substance. So when we look at latent heat, the formula here is Q is equal to mL. It's not in the data sheet. It's one of those ones that you need to remember the equation for. Already we know the values for Q and M. Q is energy, either being input or output, going in or being released. M is the mass of the substance. And L here is the latent heat of fusion or vaporization. In this formula, energy, as always, is a measurement of joules. Masses of substance, always in kilos. And thus the latent heat of fusion or vaporization would be joules per kilo. However, a lot of the time you will see the latent heat being expressed as kilojoules per kilo. What this means is you either need to do a conversion for this latent heat of fusion value, or you could technically change the energy value to be kilojoules to match. It's probably recommended that you change the energy value. You'll get a little bit more consistency there. So specific latent heat, again, this kind of data you don't see in your data sheet. If you do need it, you'll be given those values unless you're being asked to calculate for the specific latent heat value itself. Now, the reason why we have one for fusion and one for vaporization is that the amount of energy that's input for every kilo to get a substance to either melt or boil or evaporate is going to be different. So this heat of fusion is related to melting and freezing, heat of vaporization related to evaporation and condensation. Something we should note here is there is significantly more energy which is required to cause a state change from liquid to gas, and we can see that pattern for all of these, compared to the amount of energy required to cause a substance to melt. We should also note here that for each different substance, the specific latent heats are different as well. So really simple practice question just to sort of play around with the key concept. To begin with, we have a 206 gram sample of aluminium. It's being heated to its melting point. We then need to calculate the amount of energy that's required to completely melt the sample if its latent heat of fusion is 396 kilojoules per kilo. What I'm going to do first is extract all my key data. Note that I converted my mass of aluminium to kilos to match my specific latent heat of fusion. From here, we're just going to use our Q equals mL formula. There's no solving that's required, so we can just substitute immediately. So note here that I've calculated the answer as 81.576 kilojoules. And this is because of the latent heat of fusion that we were given in the question. It's in kilojoules per kilo. meaning that the number that I calculate at the end is going to be in kilojoules because, again, those units of measurement have to match. However, just because I can, not that the question's asked for an answer in any way, I'm going to give the answer in joules. I guess it's a bit of a safe bet because joules is our SI unit. Note here that I've also given my answer to 3 significant figures to match the significant figures given in the data in the question. Thank you very much. In the next video, we're going to start looking at wave concepts, which is the major component of this module. So we're going to start by looking at the properties of waves from a qualitative perspective. Until then, have a good one.